Huisman, team leader human factor at MARIN, and Willemijn Pauw, senior project manager, research coordinator at MARIN. The stage is yours.
Thank you. Okay, it's a dual presentation. I'll do the first half. Willemijn will take the second half. Unleashing the power of the crew. Are we in the wrong conference? We'll prove not to. High-tech, AI, it's always meant to support a crew. So, how do you integrate a new technology solution having the crew involved? That's basically what we're aiming at. While preparing this presentation, we came along in this tweet from Elon Musk, the believer in high-tech, and even he admitted you can go too far in automating. It was a mistake, as he indicated himself, and he underrated the humans. In this case, it was the production of the Tesla Model 3. So, we will try to explain a case we have been working on at MARIN. Here you see a hotel boat. It's a vessel with about 100 rooms for technicians, and those technicians are installing wind turbines on the North Sea. In the morning, the vessel will go from wind turbine to wind turbine, bring the technicians to the turbine, do the installation work, and at the end of the day, the vessel is returning and collecting all the technicians from all the wind turbines. Since we have to install an enormous amount of wind turbines on the North Sea, speed efficiency is key in this operation. So, not only in this calm sea, landing near a wind turbine is essential, but also in all conditions. So, how can we support the crew in making a landing next to a wind turbine? And if you look at the movie here, the technicians are walking over this walk gangway from the vessel to the wind turbine. This film was made from the perspective of the vessel. The vessel is moving, the pylon is stable. So, if you look at the tasks, and Jos indicated this morning, zoom in at the tasks. The task of the crew is to have the gangway stable on the pylon of the wind turbine. Then you need to have the ship motions within limits. The waves are uncertain, and the only parameter they really can influence is the heading. So that's a complex task, to control your heading with the effect that the gangway is stable near the pylon. So the question was, how can we support the crew in selecting the optimal heading for a safe gangway operation for the technicians? And the goal was, of course, to have that technology introduced in a way that it's not a surprise. You don't want to add technology in an operation which leaves the operators with the question, what on earth is going on? It shouldn't knock you off your feet. It shouldn't be a complete surprise what's going on. So, our approach is not only the machine we're introducing, we have a human, and we have a procedure. And it's this triangle we were focusing on during the whole iteration and the approach of this project. Between the machine and the human, there's of course the human-machine interface, have a nice interface. That's quite obvious. But if you add technology supporting the human, there's a responsibility question. And it was rather late in the whole process that we had discussions about the responsibility. If the system indicates a red indication, is that an advice to the competent crew? Or is it a requirement to abort the operation? So you can have a very nice machine, a well-trained human being, But if the procedures and the responsibilities aren't clearly defined, you still end up in a unworkable situation. So we used the human-centered design approach. It's not rocket science, it's even an ISO standard. I'm not going through the whole diagram, but we're starting with understanding the operation. Then get the user requirements clearly. Then we can step on to step 3, having a prototype and doing an evaluation in step 4, either on board or in simulator, and in this case we did both. So, looking at the first one, have a good understanding of the current operation, because you're adding technology to an operation which is in practice for a couple of years already. So it's not starting from scratch. A colleague of us spent 1 week on board of a vessel, really understanding what's going on. That was a very essential step, because the operation in reality was different than was written on paper, as it always is. Then we had a workshop with the crew, the developer of the tool, and the company office. And then we came to the next step. And the first question was, who is the user? And the answer was, yeah, it's the crew. Okay, who is the crew? On board you have the captain, the DP officer, the deck equipment officer. 3 guys, 3 roles. But there's also the customer, who is not a seaman, who is responsible for setting up all those wind turbines. Not interested in sea conditions, etc., just interested in getting those technicians on the wind turbine. And there's the office. Then we asked, what's the purpose of the system? And we had different answers. It's safety, it's efficiency. No, I just want to have a tool which can report afterwards what happened. And once we had the discussions, who really are the users, which appeared mainly the DP officer, that makes it a lot more clear what to develop. What's the purpose? It's efficiency, clear. Then you can think about, okay, what kind of system do we need? What kind of procedures do we need? What kind of training is required? And what kind of support do we need? After this step, we could go on defining a prototype. And that's up to Willemijn.
Yes, stepping in, taking over from Hans. The prototype development, I think I can explain a bit further here. What is actually the challenge that the crew has to take? Which things do they take into account to find this optimal heading next to this turbine? There's a lot of things that they have to consider there. It's the locations of the landing platform on this turbine. There's a few positions where there's a gate. There's the orientation of the nacelle, where the blades of the turbine are. There's some restrictions in that. There's a blow-on or drift-on situation should be avoided, and there's and of course these visual gangway motions that they have to interpret. And if the waves are coming from one direction, or if there's not so much waves, that one is not so difficult. But if you have a wave from one direction and a swell from another direction, it's getting much more complicated, especially if the swell is low. It's difficult to see it under the sea, but it is close to the roll natural period of the ship. So can we take these effects all into account and provide advice on what is the best heading? So we have, this is an example of an interface in which you see with the orange and green and red, you can see the excursions of the gangway of this walking bridge. And on this, you can clearly see that in the green, when the heading is chosen on the green one, then the excursions are smallest, and that in this case that would be the favorable one. So if you want to make something like this, very high over, this is the way it is approached. So on the input side, you need information about the layout of the landing platform on the turbine. You need information on the planned activities, so an itinerary, and you need information about the waves. And here you see a 2D wave spectrum with one C in it. This is input to a calculation model, and then you have the information to present the gangway excursions. If I now go step by step through these 3 steps, then in this project we work together with NextOcean and also with Radak. They both have wave measurement systems, which are really the state-of-the-art technology. So with the image from the radar, they can calculate the wave field at that moment, and then not only the main directions, but also the components of sea and swell, the directionality and the effect of the period, which are all very important to calculate the response of the ship. And then inside the core, there's a numerical model. In this case, it's a physics-based model, which we compared and calibrated with a lot of measurements that were done on board. We had more than 3 years of measurement data from motions of the ship, consumed power, a lot of information. The wave heights in the anti-roll tank, for those who know who it is. So we could use this all to calibrate this physics-based numerical model. That physics-based numerical model is changed to a somewhat simplified model, which could run inside the tool very fast and effectively. And if you then look at how do those combine, here you see a few graphs on that side. You see if you just use the HS and TP from a buoy and combine it with this numerical model, and on the vertical axis you get the forecasted motions, on the horizontal axis the motions actually measured on board the ship. You see there's a lot of spreading. If you take into account the 2D spectra from InfoPlaza, the spreading is already a lot reduced. And if you take into account the NextOcean or the Radak actual wave measurements taken on board of the ship, you see that the match is a lot better already. So there's still a lot that can be done better, but you see already that this is making big steps. So going back to this graph, apart from only knowing what you can do on that moment with that turbine, you also want to be able to make a planning, and that is in the interface in the lower plot, where it's 24 hours presented in the different headings, and you can see which headings are possible to do and which ones aren't. And then already in an early planning stage, you can decide to move to a different landing platform, and this could make the process a lot more smooth. So, I think there are 3 factors contributing to the success of this project. First of all, you have to bring the right people together. Personally, I really like to take the role as integrator, and MARIN, as independent research institute, is in the perfect position to facilitate this. Secondly, the technology under the hood of the tool should be right and reliable. It should accurately represent the response of the ship. From this ship, we have a lot of onboard measurement data which we could use to tune and validate the numerical model. And last but not least, it is very important to engage the end users of the tool in the development of it. So it's very important to realize how the tool is used, which information should be in there, and how it fits in the process on board. We had multiple visits on board, we had sessions with the crew on shore, and also an extensive session in the MARIN simulator. Yeah, so this is basically capturing a bit the 3 and 4 from the human-centered design, as Hans was illustrated at the start. Then this is next.
My experience,
the
with this app is
from
that
the
it will be
crew
helpful
in the
tool
simulator.
both for the client as for the marine crew.
This application gives a great insight and great schedule in which turbine and which team should connect and transfer when, which gives a great overview in general.
So we were really happy that it didn't start like this, the mood, let's say. So a future technical core, the example that we showed here was a physics-based model, and that's not what we are discussing here. And I think there's a lot of technology. Technically, there's more and more possible. Here you see an example where we, in our basin in Wageningen, we trained an optimist to sail by itself. We thought sailing an optimist is very intuitive. If a child can learn it, can we use AI techniques to sail an optimist? So that proves there's more and more is possible, but the challenge is to effectively integrate this in the operation and with the crew. And we think that this human-centered design has proven to be a very powerful methodology, and it can help you to do it right at once. So in small loops, iterate and make it better in steps, and involving the crew in that design process. So yeah, this is summarizing: get the right people involved, working together towards the same goal. Iteratively design a reliable and good technology, and engage the end users in the design cycle. So that was what I wanted to say.